All right, let's dive right into this explainer. We usually picture our blood vessels as a simple series of static tubes, kind of like the copper pipes hiding inside the walls of a house. But the reality, it is far more magnificent. What you've actually got inside you is a brilliant, adaptable plumbing system that is constantly shifting, stretching, and calculating just to keep you alive. To break this all down, here's our agenda for today. First, we'll look at the body's plumbing system as a whole. Then, Section 2, the arteries, our high-pressure distribution network. Third, arterioles and the great pressure drop. Fourth, the veins as a strategic blood reservoir. And finally, number 5, how the venous pump helps us defy gravity. Okay, let's jump straight into Section 1, the body's plumbing system. 40 billion. Yeah, billion with a B. Take a second and just let that mind-boggling number sink in. That is the estimated number of tiny capillaries your body uses to filter and diffuse nutrients right to your tissues. But what's truly amazing about this is the sheer efficiency. At rest, only about a quarter of those capillaries are even open and flowing with blood. The rest, they're just closed off, sitting in reserve, ready for the exact moment you need them. So, to really grasp how this all works, we've got to talk about hemodynamics. That's essentially the study of the physical laws of blood circulation. It proves to us that our circulatory system isn't just some rigid container. Both the content, your blood, and the container, your blood vessels, are constantly responding to the physical laws of fluid dynamics, as well as your body's shifting metabolic needs. Just picture how this branches out. It's like a giant, sprawling tree. You've got a single massive vessel like your aorta splintering off into a vast network. Because of this massive arborization, a single tiny capillary handles a flow rate that is literally 10 billion times smaller than the powerful flow rushing right out of the aorta. It's just a masterclass in distribution design. Moving right along to Section 2, arteries, our high-pressure distribution system. Now, the structural contrast between these vessels is absolutely crucial. Arteries are built with incredibly thick, strong walls, and they literally have to be just to handle the explosive cardiac force of blood being pumped straight from the heart. Veins, on the flip side, operate completely differently. They are much thinner and about 8 times more distensible, meaning they stretch super easily to hold extra volume. Those strong arteries actually flex and distend with every single heartbeat. Think about a classic blood pressure reading, say 120/80. Your arteries take that intense 120 millimeters of mercury systolic pressure wave, absorb it, and dampen it. Because they're so compliant, by the time the blood finally makes its way down to the delicate capillaries in your tissues, that violent pulsing has been totally smoothed out into a nice, steady, continuous flow. Okay, on to Section 3, arterioles, also known as the great pressure drop. It's incredibly common to assume that the smallest vessels, the capillaries, must naturally cause the biggest drop in blood pressure just because they're so narrow. But actually, scratch that, it's a total myth. It's the precapillary arterioles, located just upstream, that drastically cut the pressure. They take the absolute brunt of the force to protect those delicate, fragile capillaries downstream from just bursting under high pressure. So how exactly do they pull this off? Well, they achieve this massive pressure drop because their aggregate resistance is just huge. You've got millions of them acting in parallel, and their thick walls are lined with vascular smooth muscle that can dynamically constrict or dilate. This allows them to expertly dial in the local pressure precisely where and when your body demands it. Which brings us to Section 4, veins, the strategic blood reservoir. When you look at the real breakdown of blood volume, it completely shatters the illusion that your blood is evenly distributed. We kind of just assume it's spread out equally everywhere, but a whopping 64% of your entire blood volume is just sitting in your systemic veins right now. Seriously, your veins aren't just return pipes, they're acting as a massive strategic storage reserve. But that massive storage capacity begs a pretty fascinating question. If your veins are holding all this blood, how does our plumbing adapt to sudden, massive volume changes? Like, what happens to the whole system if a patient gets a massive blood transfusion and takes on an extra half-liter of blood in just a few minutes? Well, the answer lies in a brilliant concept called delayed compliance, or stress relaxation. When extra volume is suddenly dumped in, the pressure spikes at first, but then the smooth muscle fibers in the vein wall begin to slowly creep and stretch out to longer lengths. Over a period of minutes, the pressure safely drops right back down toward normal. It absorbs that extra blood without stressing out your heart. And it's not just your run-of-the-mill veins doing this. Your body has evolved highly specific emergency reservoirs. You've got large veins in your abdomen and liver that can hold hundreds of milliliters. But the real star of the show is the spleen. The red pulp of your spleen is essentially a giant sponge for red blood cells. If you start bleeding and your blood pressure drops, your sympathetic nervous system tells the spleen to squeeze. It can instantly push up to 50 milliliters of pure, concentrated red blood cells right into your circulation to give you a sudden, life-saving boost.
All right, last up, Section 5, defying gravity with the venous pump.
Because we are upright creatures, we've got a bit of a gravity problem. When you're standing up, hydrostatic pressure, which is the actual physical weight of the fluid inside your vessels, is aggressively pulling the weight of your blood straight down toward the floor. The physics of this are honestly pretty startling. If an adult just stands perfectly still, the gravitational pressure in the veins of their feet skyrockets to roughly 90 millimeters of mercury in just 30 seconds. If left unchecked, that high pressure would cause fluid to leak straight out of the capillaries. Your tissues would swell up, and your total blood volume would drop so fast that you could literally faint within minutes. So, what is the evolutionary fix for this gravitational nightmare? It's the venous pump. Tucked right inside your veins are these tiny, mechanical one-way valves. As you walk, shift your weight, or even just tense your leg muscles, you are literally squeezing those veins. And because those valves only open in one direction, that squeezing forces the blood back up against gravity, step by step. This keeps the pressure down in your feet safely capped below 20 millimeters of mercury. So, I'm going to leave you with a quick thought to ponder. The next time you simply stand up from a chair and walk across the room, will you remember the 40 billion microcontainers, the highly distensible reservoirs, the pressure-dampening shock absorbers, and the intelligent one-way muscle pumps all working in perfect unison just to keep you conscious, balanced, and moving through the world?